Hey class, today we're going to start section 2 in chapter 5, and this one's called electron arrangement in atoms. First, before we get started, section 2 builds off of section 1. So on the next slide, I'm going to present you with information that is all located within section 1. It is not located in section 2 part of the notes, so if you want to write it down, you can, but just know you don't have to. This is just purely review. So for review, we have to understand that outside of the nucleus, there are different levels upon levels. And we talked about how it's kind of like a hotel. You have a hotel room floor, then within the floors there are different rooms, and then within the different rooms there are different amounts of beds based on the configuration of the room, and then inside the rooms there's going to be people. Same thing happens in an atom. We have energy levels. And we represent that by the principal energy level with the letter N. So N equals 1 means energy level 1. N equals 3 means energy level 3. Inside those energy levels, there are different sublevels. So S, P, D, and F are the 4 letters that we use. So you can think of these as different types of rooms on a hotel room floor. Was it a single room, a double room, a king size, etc.? Within those sublevels, each of them contain a different number of orbitals. So, for example, S always has 1 orbital, P will have 3, D will have 5, and F will have 7. So you can think about this as how many beds are in a room. For example, a single room might have 1 bed, a double room might have 2 beds, a king room might have a king bed and a pull-out couch. So we can think of it that way. And then 4. Since each orbital can hold 2 electrons, you're just going to take the orbitals and times it by 2 to get your number of electrons. When we played the Kahoot, you might have heard me make statements such as orbitals are going to be half the number of electrons, or electrons are double the amount of orbitals, because there is a relationship there. So respectively, S is 2, P equals 6, D equals 10, and F equals 14. Again, in our hotel scenario, we can make the analogy that electrons are like people sleeping in those rooms. So we're going to actually tie this information into something new called electron configurations. And if you think of the word configuration, that means how do you arrange things, like a room configuration. How are things arranged? This is an electron configuration, and so it's defined as how electrons are arranged in these different orbitals around the nucleus of an atom. The shorthand notation is going to be usually represented by a number in front, and that tells me my energy level. So this can be a 1, 2, 3, 4, etc. Then it's going to be represented by a letter, and that letter is going to tell me my subshell, such as S, P, D, or F. And then we have a superscript, and this superscript is a little number that's going to actually tell us the number of electrons that are in this orbital. Before we can write the shorthand notation, we have to understand and look at the visual representation. And we call these visual representations of electron configurations, we call them electron box diagrams. So over here, I have electron box diagrams for 5 different elements: hydrogen, helium, lithium, sodium, and oxygen. Up at the top, these up here represent, again, this number 1 represents the energy level. The S represents the orbital. 2 is the energy level 2, an S orbital. Energy level 2, a P orbital. The other thing we have to understand about electron box diagrams is what do the box and arrows mean? So a box actually represents an orbital. So you're going to notice if you're an S, you only have 1 box because S's only have 1 orbital. If you're a P, you're going to have 3 boxes because they have 3 orbitals. And you're going to notice D will have 5 boxes because it has 5 orbitals. Now each arrow represents an electron. Each box can hold a max of 2 electrons. Does that mean they are going to hold 2? No. They can have less than 2, but they can only have a max of 2. Notice that if you're an S, you have 2 electrons. For P, you can have a total of 6 because you have 3 boxes. 3 times 2 gives me 6. And D, you're going to find out, can have a total of 10 arrows in them. So how do we write electron box diagrams? What are our rules? So there are 3 rules: Aufbau's principle, the Pauli exclusion principle, and Hund's rule. And all of these are going to show you how to draw these electron box diagrams. Let's start off with the first rule, which is Aufbau's principle. According to Aufbau's principle, electrons are going to occupy orbitals of the lowest energy first. And one thing we have to understand about the lowest energy is this is going to be the one that's closest to the nucleus. So once you get away from the nucleus, you're going to go from increasing order. So energy level 1, sublevel S. Energy level 2, sublevel S. Energy level 2, sublevel P. And you're going to keep filling these electrons as we go up and up and up. However, you're going to notice towards the top here, some of them appear to kind of be around the same energy. So 6s, 5d, and 4f tend to be closely around the same energy. And you might be like, well, why is a 6 looks like it's slightly less than a 5? And that's because energy levels, when you get to higher energy levels, can overlap each other. So again, overlap. So how do I know the order for these energy levels? Because I don't think you want to memorize 1s, 2s, 2p, 3s, 3p. You don't want to memorize that order. So I gave you out this periodic table the other day in class and told you keep it because you're going to use it a lot. If you can use this periodic table, you will be good and will never have to memorize the order in which those energy levels happen. And the whole part of this is read it like a book. Just like a book, you're going to start in the upper left-hand corner. So here you are written 1s first. Even when you go over here, it's still 1s. So notice down here, 1s is written first. When you go to the next line, you see a 2s. So a 2s is written. Here you have a 2p. That's a 2p. Once you get to 2p, you got to start at the next line. So we have 3s, 3p, 4s, 3d, 4p. Notice, the order you read it is the order that you see it down here. The only ones that get a little tricky is 4f. 4f will actually be read after 6s, and 5f will actually be read after 7s, because that's just where they go on the periodic table. In terms of this, you will always have access to this, so as long as you know how to read it like a book, this is how it's going to work. Again, if you read it first, it's going to have the lowest amount of energy. Anything you read after will have higher energy. So for example, if you were trying to compare 3D to 4P, 3D would have the lowest energy compared to those two, and 4P would have higher energy. So you're going to also notice these written up the top are written in the order of lowest energy to highest energy. Again, these electrons are going to fill the boxes before it can move to the next one. Again, it fills the lowest energy first before it moves to the next box. The second rule is called the Pauli exclusion principle. And basically all this says is that orbitals contain at most 2 electrons. However, those 2 electrons are not going to be placed the same way. Electrons are spherical, and so therefore they have something called spin. Electrons, if they are going to be paired up because they have the same charge, they're going to oftentimes have opposite spins, and we represent this using arrows. We use one arrow pointing up and one arrow pointing down. And in case you were curious what spin meant, it's just a mechanical property that electrons have. They can spin clockwise or counterclockwise. And again, like I said, we represent these with arrows. So oftentimes, if you're going to put arrows in a box, you're going to see one arrow pointed up and one arrow pointed down. So if I go back to this picture, we have noticed we have one arrow up, one arrow down, one arrow up, one arrow down. They will always be written that way. The third rule is the rule that people usually mess up the most. So this is called Hund's rule. And this is saying that when electrons occupy orbitals of the same energy, they are going to make the number of electrons with the same spin direction as large as possible. So let me kind of explain this and make sure that if you have questions you're asking. Say that I wanted to place 4 electrons within a 2p energy level. Oftentimes, people will misplace these. People will say, oops, I have to have 3 boxes because I'm a 2p. Oftentimes, people put one up, one down, one up, one down, and say, oh, I have 4 electrons. But according to Hund's rule, we cannot place them that way. If you were going to place them correctly, you would have to put an arrow up in each box first because we want as many arrows going the same direction. Once you get one in each box, then you are allowed to pair down. So here, now you are allowed to pair down. So let's look at this with oxygen. Oxygen, it says, has 8 electrons, and I asked my class, why does oxygen have 8 electrons? And that's because its atomic number is 8 on the periodic table. It has 8 protons, and protons equal electrons for neutral atoms. So you're going to have 8 arrows. My 1s is going to get an up and a down because there's only one box. My S is going to have one up and one down because there's only a single box here. However, for a 2p, there are 3 boxes. Each of these 3 boxes have the same energy. They all have a 2p energy level. So you have to put an arrow up in each box first, and then you are allowed to pair down. Another example is here up over here 3p. All 3 of these boxes have the same amount of energy, so you would have to put an arrow up in each before you are allowed to pair down. Same thing with a 3d. All 5 of these boxes have the same energy, so you would have to put an arrow up in each box before you are allowed to pair down. So we're going to focus on phosphorus, and we're going to draw this electron box diagram. First, we have to understand that phosphorus is letter P on the periodic table, and therefore it has 15 electrons that we are allowed to use. Again, 15 is its atomic number, so it's its electrons. We're going to look at the first box. 1s is only one orbital, so we can immediately pair up and pair down. Once you fill the 1s, you are allowed to move to the 2s. There's only one box, so we're going to pair up and we're going to pair down. Then we get to a 2p. Now this one has 3 separate boxes, so we need to pair up, and if I have enough electrons, I can pair down. I've only used 4, 5, 6, 7 electrons, and I need 15, so I have enough that I can pair down. So right now I've used 2, 4, 6, 8, 10. I have 5 more to go. This one is only one box, so you can pair up and pair down. That gave me 12. I have 3 left to go. If you're in 3p, notice there are 3 boxes. We have to put an arrow up in each first before we are allowed to pair down. You're going to note that when you put an arrow up in each, I've used 15, so I do not have enough to pair down, so I stop. So that is the electron box diagram for phosphorus. Now, drawing electron box diagrams can be very tedious, very time-consuming, and no one wants to draw all those arrows. So there is a shorthand method for showing electron configurations by writing out the following kind of shorthand below. And I kind of introduced this to you when I gave you the definition of electron configuration. Again, it involves writing the energy level first, followed by the letter that represents the sublevel, and then a superscript that is going to represent the electrons within that sublevel. So, for example, let's look back at oxygen again. Oxygen, we can, instead of writing out this whole box thing, we can shorthand it by saying 1s. There's 2 arrows, so we gave it a superscript of 2. 2s, we write 2s, and then there are 2 arrows, so 2 for my superscript. And then we're going to write 2p, and then since there are 4 arrows, we're going to write 4 for our superscript. Notice that 2 plus 2 plus 4 equals 8, which is how many electrons oxygen is allowed to have. So note, the sum of the superscripts is going to equal the number of electrons for that atom. And I think that's pretty cool. So let's use phosphorus for example. Now we already did the box diagram, so let's actually write the shorthand electron configuration for it. Again, we're going to write it. We see 1s first. We drew 2 arrows, so I'm going to draw 2. Then we have 2s. We have 2 arrows. We have 2p. Notice I have 6 arrows in there. Then I have a 3s. There are 2 arrows. And then I have a 3p. Now p Subshells can hold 6 electrons, but this one only has 3. So this is going to be a 3p3. And then you are done. You do not write 4s because there are no electrons there. What if you didn't have the electron box diagram? Again, you can use this periodic table to tell you the energy level order. And we're going to use gallium as an example for this. So the atomic number for gallium is 31, which means it has 31 electrons. So we're going to write the electron configuration for gallium. Again, if you're going to read this like a book, top left-hand corner, we have a 1s. So we're going to write 1s. We should know that S's can only hold 2 electrons. Again, the way we're going to know that it only holds 2 is because I have 1s, 2s, there's only 2 boxes for them. Or sorry, 1s and 1s, there's 2 boxes for them. After you fill the 1s, we have a 2s, and there's 2 boxes for them. So, a 2s2. After that, we have a 2p, and notice I have 6 boxes, so I can fit 6 electrons. So a 2p6. After that, we have a 3s and then a 3p. So 3s, which can hold 2, and then a 3p, which can hold 6. I'm going to go ahead and count my electrons to make sure that I don't go over 31. So 2 plus 2 is 4, plus 6 gives me 10, 12, and then 18. So I've only used 18. So I need to keep going. After 3p, so here I have 3p, I'm going to start at my next row, which is 4s and then 3d. 4s can hold 2 electrons, because s's will always be 2. Well, max of 2. Then we have 3d. Now d's, if we remember, can hold 10, but if not, you can go and count. Let's make sure I didn't go over 30. 2, 4, 10, 12, 18, 20, 30. So I'm at 30, but I need 31, so I have to keep going past 3d10. If I look at what's after 3d, we're going to see that 4p is next. So I'm going to write 4p. P's can hold 6, but you can't go over 31. We only have 1 electron left, so this is going to be a 4p1 because I only have 1 electron left. And that is the end of today's lesson. If you have any questions, please make sure that you ask. And otherwise I hope you have a great day.